Aquí debe ser, ¿no? Ya lo perdiste. For different groups.
Welcome, everybody. Before starting, I just want to introduce you Eduardo Colombo, who is coming from Rio de Janeiro. He's a student there with Australian informed, and he will be with us until September, working on problems of biological growth, crones and pathos for people population. Welcome.
Thanks, Emilio. Good afternoon, everyone. In the name of the whole institute, and also in the name of the organizers, Jorenz and me, it's my pleasure to welcome you to the first Colloquium of Excellence for this year. The Colloquia of Excellence, as you know, are a series of seminars where we try to get eminent speakers which are really working at the forefront of complex systems. And we're very happy that we again could win really outstanding speakers for this year, particularly since this is a special year for us in IFISC. So we'll have 9 Colloquia of Excellence this year, spread all over the year, 5 of which actually will take place in the context of the Crossroads in Complex Systems conference in June, and many of the organizers of that conference are sitting here in the audience. So it's my great pleasure to introduce the speaker of today, Professor Herrmann from the ETH in Zurich. And what impressed me most when I was going through his CV is that he's not only working on nonlinear systems, but that he also has a very nonlinear CV, at least. It was not easy for me to follow all the very interesting paths. So he was born in Cuba and raised in Bogota, but studied physics then in Germany, in Göttingen, Cologne. And he got his master's, he got a diploma and PhD there on topics of solid-state physics and on statistical physics of critical phenomena. From there he moved to France, to the Service de Physique Théorique in Saclay, and became member of the CNRS, where he made it to the Directeur de Recherche Première Class position, and which he still holds. From there he went to Germany in 1990 and was head of a many-body group in KFA Jülich. And from there again he went back to France, to an École Supérieure de Physique et Chimie Industrielle, and was head of an institute there. And in 1996 he became full professor and director of the Institute of Computational Physics at the University of Stuttgart, so we're back in Germany. From there, he did not go back to France again, but this time to Switzerland. So to the ETH in Zurich, where he's a full professor for theoretical physics at the Institute for Building Materials since 2006. Right? He's also at the same time a guest professor at the University of Fortaleza in Brazil, where he spends part of the year of his work. So he has received an impressive amount of recognition and prizes. So he's a Guggenheim Fellow, he's a member of the Brazilian Academy of Science. In 2002 he received the Max Planck Prize, in 2005 again the Kastler Prize, and he's a managing editor of the International Journal of Modern Physics and Granular Media. And he has co-authored more than 400 articles. What impressed me most about that there are more than 60 articles among them which have been cited more than 100 times, which shows really the breadth of the work that he has been doing. So after his PhD, he, for example, worked on gelation and irreversible growth. He even built a special purpose computer, which I find very interesting, to calculate the conductivity of percolation clusters. He studied fracture of heterogeneous materials, granular media, and he himself considers the highlights of his research the construction of space-filling bearings and the establishment of equations for the motion of tunes. His present research topics are in dense colloids, formation of river deltas, quicksand, and the failure of fibrous and polymeric composites in complex networks. So we're very happy and honored to have you here. Looking forward to your presentation.
So Ingo, you were hired as my public relations manager. Thanks a lot. I'm going to start this, everybody. I'm very happy to be here. Thanks for the invitation. It's the first time I'm in Mallorca, and I heard so much about this institute already, so it's a very important day for me to get a chance to see my friend Maxi and Raoul, etc. We know each other since 30 years ago. Good. So I am going to talk about a very specific subject here. This was what you chose. I gave you several options, and you chose this one. And since this is a percolation talk, I will be forced to explain a little bit about percolation, because I heard that many of you are not so familiar with this field, so I will take a step backwards. But first of all, I would like to briefly introduce my collaborators. So here you see four professors: Suarez from Fortaleza, Bob Ziff from the United States, Myung-Yang Kang from Korea, and Peter Grasberger, who is now back in Germany. And then I have here two PhD students, Julian Schrenk and Cho from Korea, and finally one Portuguese professor and then one Brazilian professor who just became professors, both of them. They were postdocs at the time, but this work was done. Good. So, as I said, percolation is, of course, the basis of my talk, so I will have to a little bit describe what exactly it is. So I'm apologizing to all the experts in the field that I will be a little bit boring here. So in percolation, you start with a graph, which let's say is a square lattice, for instance, and you occupy sides of this graph, or nodes of this graph, randomly and independently from each other, and you define a neighborhood by nearest neighbors, for instance. So if two nearest neighbors are occupied, they are connected. They are supposed to be connected. They are nearest neighbors and occupied. And so then in this way, you can create now defined clusters as the units of mutually connected sites. So cluster here is of site 1, and here clusters of different sizes. And then when you increase the probability of occupying a site, then your clusters become larger and larger. For small probabilities, they are small, 0.2. And when you go larger and larger, the clusters become larger until the percolation occurs, which is when a cluster appears which spans the system. It means a cluster that you can start on one side and you can walk on top of the cluster and you reach the other end. This is what is called a spanning cluster. And so the appearance of the spanning cluster is the onset of percolation, the transition of percolation, and above this value, which is on the square lattice has a value of 0.592745, etc. Above that, you have a spanning cluster, a percolating phase, and the transition between the two, the percolation transition, is a classical example of a second-order transition. It is a part of the Q-state Potts model, Q going to one limit, so it's very well established, very well proven. This is a second-order phase transition, which is described by an order parameter, as you remember, order transitions, and the order parameter in this case is the fraction of sites that belong to the infinite cluster. Where infinite cluster and spanning cluster, I will kind of make equivalent. And so the order parameter behaves like this. It is 0 in the non-percolating phase and non-zero in the percolating phase, and at the transition it increases with a power law, and the power is known in 2 dimensions exactly. And the upper critical dimension of this problem is 6 or above 6 dimensions. The exponents are all in the field. So this is a classical description of the percolation model. And as I said, these transitions are always continuous. That means that here at this point there is no jump. This goes continuously to 0. Okay, so this is well established. And now one knows that there exist many, because percolation is a very basic model. It appears in all fields, from finance to biology, everywhere when you have this problem of connecting two sides to each other. It appears all over. And there are many problems, many applications in which the percolation problem produces some abrupt transition, where you can measure, you can find, I will show you later a concrete example, the flooding and the breaking of dams, because you can consider also percolation as the filling of a random landscape. You put water inside, and you see higher the level comes, the more you connect. And if you have now dams in this landscape and they break, then the transition is not anymore continuous, but you have a sudden, let's say, breakdown. And the same kind of also, let's say, sudden transitions, percolating transitions, are observed in finance. Also in finance you can define percolating models, like when banks start to collapse and they influence each other. Or also when you talk about volcanic eruptions, because here you have the percolation of the magma through the porous medium coming up. And you know that these volcanoes, they don't flow out like continuously, you know, they flow out like explosively. So there exists certainly and also percolation transition that is first order. And the big issue that I'm going to treat here, the entire seminar is about the question, how can a transition, a percolation transition, become first order? Okay, so this is the subject. I will first show you an old case which is known to produce first order transitions, but which is good here for completeness, yes, that nobody comes up and says, but it's also an old case, which is the so-called Bootstrap percolation. Bootstrap percolation is a strange percolation, because what you do here is the following. You say, I start with a given percolation configuration, that means I occupy my site with a given probability P, and now after I've done that, I introduce a so-called culling step. Culling is written this way, yeah, in which I say I don't allow for every site having less than, let's say, 2 neighbors. And that means you remove all the sites that have less than 2 neighbors. And you have to do it in several sweeps, because once you have removed one generation, then can appear other ones that have only one neighbor, and you have to remove them too. When you do this removal, one after the other, of course you remove also many connecting links, and at the end it can happen that you don't connect at all. And what you find is that in fact, if this was the original phase order parameter, like I showed you before, due to the culling, this line is pushed to the right and ends up at 1. It means this is a kind of a trivial first order transition, because you have nothing happening until everything is occupied and then it becomes 1. This occurs for specific cases that you see here on the cubic lattice, for cases when the critical number is larger than 4, and for the square lattice when it's larger than 3. But this is, if you want, not very practically implementable. It's a very strange. This culling procedure is not what occurs in volcanoes or in financial systems. So this is why this mechanism to create the first order transition through culling is not what we're looking for. We want to have one model which immediately produces the first order transition. Okay, so this was prehistory. Now we come to the starting of history, which is the year 2009. In this year, these three mathematicians, and this guy is famous one, he has Erdos 1, so he got published together with this Erdos guy. So these are big shots. They made the paper in not anything else than Science. Yes, it was a very visible journal, visible article, in which they introduced a model which is what they say explosive percolation. They created this terminology of explosive percolation. And their model was the following. This is a product rule, also called product rule. In fact, they studied percolation on the infinite dimensional system, the percolation in mean field, which means that you put your nodes somewhere, like here, and now you have the right to connect everybody with everybody. So instead of a square lattice where you only can connect the nearest neighbors, here you have this, what is called mean field situation, or infinitely connected graph. So in principle, you can connect everybody, and now you make your filling of the occupation, or again one by one. You choose a bond, but you don't choose, in percolation you choose one bond and you occupy, one bond occupied. Here now, in the product rule, you choose two bonds, this and that, and then you ask which of the two bonds would create, if occupied, the larger cluster or the smaller cluster. And then you take the one that makes the smaller cluster. In that way, you avoid creating large clusters. And the hope is that you will avoid also creating the spanning cluster. And they did this. It was strange because they were mathematicians, but they did the simulations, they did numerical work, and this was also their fate. It was a fatal find, and you will see why. And so this is what they found. They found here, this is the black one, is what you find usually for this infinitely, this kind of mean field situation. This is the order parameter. And if you now introduce this product rule that you say, I take two and compare them and look which is the smaller cluster, I get this red line. So this is clearly, looks like a jump as compared to the other one. So they published this. It became, in the same year when this came out, there appeared another 3 physical letters only working on this. So just showing, some of them showing that they're doing the same thing as you can guess on complex networks, the other ones on square lattices, everything. So it inspired everybody to work on this field, and also inspired some other serious mathematicians. And actually,
but there should be, how many times do you do that?
You do this one all the time. All the time. You choose always randomly two possibilities.
How many times do you do that?
And you do it more and more and more and more and more times until, yeah? I mean, you come to start here, and you move, R essentially is the number of occupied bonds, and you go, and then you see, you go through the transition. So, yeah?
So, is any justification for the non-local dynamics? You're choosing two nodes which are completely random,
yes.
And they do any justification comparing to volcanoes or the...
No, not usually.
Just a
mathematical model. They had no idea of other applications. They just invented this model, and then they pretended that this is the first transition. But people started to doubt already when they looked at the size distribution at the critical, or at the transition point, at the first order transition point. You see that this is now the clusters. Every color corresponds to another cluster, and there are clusters of all sizes which is strange. If you look at the cluster size distribution, it is a power law. This is not what you expect for the first order transition, a power law. That's weird. So everybody was a little worried. And then came very soon, in 2010, 11, came 3 papers that killed the problem. These were mathematicians, all of them are mathematicians essentially, that, well, this is not this one, but here, this is, yeah. And they showed with mathematical arguments, which are rather complex and not always completely transparent, but I mean, if there are 3 words doing the same thing in different ways, then it's kind of convincing. They showed that this method, this had to be a second order transition, and they also showed that the convergence would be very slow, that you would only see this, this gap here. This gap here, sorry. This gap would decrease, and you would only see it going to 0 if you study systems of size 10 to the 24. And this, of course, for every numerical person is like a killing argument, and everybody became very scared to work on this further. Okay, but this is a very strong statement, and so this was all wrong. In other words, so finished. But then people, I mean, in the meantime, while this was kind of proven, also numerical work was done, and I show you now 2 papers that we did on this, just numerically. I mean, it's not, the problem is that we are only doubting if this is right, because we know that in the case of the infinitely dimensional system, it is wrong. But this is now, if you take, for instance, a square lattice, it can be done. So the first thing that this was invented by Suarez is that instead of taking here 2 connections, you can take m connections. And then from the m ones, you can choose which is the one that creates the smaller cluster. And so this is called the best of m model. And if you simulate this model, you find out that the transition becomes sharper and sharper, the larger becomes m. And in particular, if you go on the square lattice, which is not where the proof works, then it's even more pronounced. So I show you here, for instance, this is now what you see here plotted is the second moment of the cluster size distribution. So just one of the properties. And if you look at now how it looks like for m equals 2, for m equals 1, which is classical percolation, which 1 is all percolation, and m equals 10, you can very clearly see that for m equals 2 and for classical percolation, there is a clear dependence on the system size, yes, while here there is no dependence on the system size. And here you see the exponent is less than 2, and here it is equal to 2, which is dimension 2, and this is what you expect for first order transitions. You expect it to finite size scaling works with the exponent of d. So this makes much more sense. So this, everybody would say, wow, this is much more first order transition than that one. Yeah? So there are some hints. And the second hint we have is a work that we did also in 2011 with Bob Ziff, where we mix now the m equals 10 model with the m equals 1 model. M equals 1 is percolation. We know the transition is continuous. And for m equals 10, on the square lattice, we believe it is first order. And so if you now mix the 2 with different degree, then you might find a transition from first order to second order. And what we find is, indeed, this q is the mixing parameter. The more I mix in the m equals 10, suddenly there appears a point which has tricritical scaling. I can show you this. Well, I don't want to show too much detail, but here you can show that there is a collapse. Okay, it's a kind of there are 2 scaling parameters, and there's a crossover exponent, and they all scale on top of each other. So if you do a careful work, which requires, of course, knowing about tricritical scaling laws, etc., you find that there exists this point here, which tricritical points typically are the ones that separate first order and second order transition. So a second indication that there is a first order transition for n equals 10 on the square lattice. But as I said, all these are things which by the end of 2011 nobody believed anymore, because after the statement that you had to go to the larger systems, there was no way that you can convince anybody that numerical work was useful. Okay, so, but then in the meantime, we could also invent other models, because now the machinery was running, and so people started to invent new models. And now I show you a model which indeed does work. Namely the following. You now occupy bonds randomly, like in usual percolation, except if the bond that you want to occupy would create a cluster larger than any cluster that you have already. which is of course then a problem because this is a cluster that can become infinite cluster. And if this occurs, if you have a bond that would create a cluster that's larger than any other cluster, then you occupy this bond only with a probability given by this expression, by this Q, in which S bar is the average cluster size. So the larger the cluster is with respect to the average cluster size, the larger becomes this, and this is negative, so exponentially decreasing probability. So it means that if you create a cluster which is much too large, the probability to accept this move is essentially zero. And this way you suppress really the creation of large clusters. And when you do this now, again, unfortunately numerically for the time being, you find a very sharp transition at a very well-defined point. As compared to percolation, you see it's not so sharp. But in particular, which is most interesting, you find that the cluster size distribution is not a power law, but it's a bimodal distribution, which is exactly what you expect in first-order transitions. If you have two ground states and you have a distribution at the transition point, which is bimodal. So as compared to classical percolation, where I showed you that the distribution of cluster sizes is a power law. So this is a very good signal for first-order transition. And in addition, if you now look at the clusters, how they look like at the transition point, you see they are compact. They are not fractal anymore. And you don't see clusters of all sizes like here. This is a classical percolation, how the clusters look like at PC. And of course, there are clusters of all sizes because distribution is a power law. And you see, these kind of hierarchically embedded clusters. And here, no. Here you clearly see compact clusters, but very interesting, the boundary of these clusters doesn't seem to be so normal. The boundary of these clusters looks very fractal. And if you now analyze this,
What was the parameter alpha in the previous?
Alpha? Alpha, no, there's no alpha.
PS alpha. No, there was, yeah, in that one.
Sorry. PC, no. PC.
No, previous one. Here, P of S and alpha.
Ah, sorry, yes. Yeah, sorry, I don't know. It's,
Okay.
no, it is,
If it is not important, I was just curious.
it's the S, no, S is the
Size.
size of the clusters, and the alpha, I don't know, maybe it's discarded. Okay, so these frontiers now turn out to be fractal. As you can see here, there's a log-log plot of their lengths as function of the size of the system, and the fractal dimension is 1.2 something, 2.23, 2.26. And this gives us now an interesting hint, because this number, this fractal dimension in 2 dimensions of 1.22 rings a bell. There exists already, this number exists already in literature. I will now spend, let's say, something like 15 minutes only talking about this specific exponent. You will see where it comes from. So, but before this is in 2 dimensions. Everything I said to you in 2 dimensions, of course, can be done also in other dimensions. So here you see in 3 dimensions the same model that I discussed. And you see how the configuration of clusters looks like at the transition point in 3 dimensions as compared to classical percolation. We have, of course, many small clusters. And then in 3 dimensions also you find that the surface of these clusters is fractal, while the clusters themselves are compact, and the fractal dimension is 2.4. So we have this fractal dimension of 1.21 and 1.2.4 in 3 dimensions, which I would like to explain more. So now I come to the next step. Now we come back to real percolation, and we'll find that this exponent already exists in classical percolation, but in a different place. Namely, I will now talk about the bridges. The bridges are the bonds in percolation that if I occupy them, I would create a spanning cluster. So they are the opposite of what is called the red bonds, which are when you have a spanning cluster, which are the bonds that if you remove them, you will destroy spanning. And so here it is like before you have spanning cluster, if you put them, they will span. And these 2 kind of bonds, the red bonds and these bridges, they are dual to each other. So principally this has the same dimension. And so, okay, so these are the bridges. And now I will show you how these bridges behave. I will start to fill in bonds randomly in square lattice. I will show you square lattice. and I will occupy bonds randomly, like here. And now every bond that is connected to the top will be green. Everything that is connected to the bottom will be blue. And every time you connect some blue and some green with each other, or try to connect with each other, this is a bridge. And what you see is that if I continue occupying my bonds, at the end, the bridges, oh, this is the bad news, the bridges, they form a line, yes, which goes through the entire system, of course, yes, and this line happens to have the fractal dimension of 1.2. So here you see, oops, again, God, anyway, doesn't matter. You have seen my movie. So what you have is, at PC, exactly, the first bridges appear. And this is what you see here. So you have some bridges appearing. When you increase P, there are more and more bridges filling in. And when you reach P equals 1, then you have this complete line of bridges, which then have this fractal dimension of 1.2. So this is where the fractal dimension comes from. And yes, as I said, this is now how it looks like. You have this frontier between the bottom cluster and the upper cluster, and the bridges in between, and the fractal dimension is 1.2. Okay, and what is interesting to see is that at PC, the fractal dimension of this set of bridges is equal to the fractal dimension of the set of cutting bonds, which Cornelius has proven to be equal to 3/4 in 2 dimensions. So the fractal dimension of the bridges at PC is 0.75, but as we have seen above PC, especially at P equals 1, it is 1.2. So what we have is that the critical exponent of the size of the set of bridge bonds at PC has one critical exponent here, which is not the 1.22. The 1.22 is the fractal dimension of the bridges in the percolating phase. So not at criticality, but above criticality. There we find this exponent again. And what can also be seen is that this point, in fact, has tricritical scaling. I don't know if anybody of you knows the collapse of polymers, the theta point. There you have the same situation. You have a polymer chain in diluted polymer chain with radical interaction. Then if the interaction is larger and larger, then suddenly this polymer collapses, and there is a transition. And this transition, there is one exponent, and above the transition is another exponent. Yeah? And here we have a similar situation. So here's my occupation mobility. This is the percolation point, and now I show you the density of sites of bridge bonds, bridges, on the support of the fractal line of the TR. So that the density increases, and you see it increases with some power law, and this power law is 1/2, and this is the second exponent that you need for this tricritical scaling. So to make a long story short, this is what we find as the scaling for the bridge bonds. So NBB is the number of these bridge bonds, and then L is the system size, PC is the critical threshold, and this zeta is this zeta here. So there exist now, if you want, 3 exponents, the 1 over nu, the dBB, and xi, 3 independent exponents. This is what is called the tricritical point. So we have this scaling law, and you must remember this, because now later I'm going to use the scaling law for some analytical argument. Okay, and now in higher dimensions I can do the same thing. So in 3 dimensions I can also do percolation, and I can obtain the set of bridge bonds, and now form a surface, and the surface is fractal with this dimension, so everything works well. And then finally, if I go to higher dimensions, I come to 6 dimensions. As I remember, 6 dimensions is the upper critical dimension of percolation. So above 6 dimensions, the set of bridge bonds is dense. It means the fractal dimension of the set of bridge bonds is equal to D. And below, as you see, the value goes down to, let's say, 1.22 in 2 dimensions. Okay, what I should also say, this is maybe interesting for generality, is that this exponent 1.22 appears in many other places of physics also. For instance, the watershed. If you take a random surface, that means you put random numbers on every side of a square lattice, and then you ask, it is raining, the water flows always down, you have a system with the left quarter and right quarter, you ask, does the water flow out to the left or to the right? If I put a drop on this position, where does the drop go? You find there is a line, a line dividing the two hydraulic basins. And this line is called the watershed. So everything here goes to the bottom and everything here goes to the top. And this line here, on a random uncorrelated surface, has also the factor dimension of 1.22. And you can show that these 2 points are equivalent. In fact, this is related to the problem of the dams. Sorry. You see, this is now a random surface, and I fill in water. I told you this is a percolation problem because the higher the water level, the more, let's say, I have wetted. When I now increase now the height, I reach the percolation threshold, and then the water flows on the other side. And then every time the water flows on the other side, I block the side on which it spilled over. And so I block every side on which something spills over until I reach along, you see, until I have a, sorry, again, it doesn't stop at the right time. But you see that each time when the water spills over somewhere, you create a dam. And so this dam becomes longer and longer. This is the red line. This is a very, very long dam. And finally, is identical to the watershed. You see this wall, this red wall corresponds to the watershed. And so here you see the picture I started with when I said that a dam produces abrupt percolation transition. If now I destroy one of these red points here, then immediately everything that is here will be completely filled with water. So you see very clearly the relation between the 2 problems. Okay, but there are other things which are in the same universality class. For instance, if you study loopless percolation which you don't allow to close loops, then this line 1.22 is exactly the shortest path that you have on top of the percolating cluster. Or another application is if you have 2 fluids invading a porous media from opposite sides. And both fluids have the same viscosity. Yeah? That they both have on the same pressure gradient. When they touch, they will invade from both sides, and there will be a line in which they will touch and stop moving. This line, again, has factor dimension of 1.22. And finally, I should mention that this path, this loopless path of defined watershed path, also follows the so-called Schramm-Loewen evolution. I mean, at least it has been shown numerically, yes. It follows all the properties of left passage probability or winding angle, etc., which are known for SLE. So this is, let's say, just to give you a little general information about what this exponent is all about. Okay, and the exponent has been calculated with very high precision numerically in the past. So you see here, this is for different systems, shows the universality for different types of lattices. And here you see, by introducing corrections to scaling, you can finally get very high precision on these numbers in 2 and 3 dimensions. Okay, so that's the exponent is very well understood. And now let us come back to my next progress in this field, namely a model that we invented now together with these Korean people. And they were lucky to get into science also, because it was a paper which solved the problem of the old paper, so this is why we got into science. So here now, we're using everything together. We do again a model for the time being, let's say with m equals 2. That means that I choose 2 bonds, and now from these two bonds, or m bonds in general, I ask, is there any bridge among these bonds? And if there is any bridge, then I do not occupy the bridge. I occupy randomly any other bond which is not a bridge. Unless all bonds that I have, I mean in this case 2, were bridges, then I have to occupy one of them. This is the model. So, as I said, this is for m equals 2, but the model is defined for arbitrary m. And so what you see here now is what happens numerically. Here the red line, this is the old order parameter of the classical percolation model. Yes? And now this is essentially m equals 1. Now we take m equals 2, you see there is a jump up to here. M equals 3, this jump goes to the right. M equals 4, the jump goes more to the right. Yes? And so this is very encouraging. But now what is discouraging is if you change the system size. If you change the system size, this line moves to the right, to the left. No, to the left, yes. And so it looks as if it goes to percolation. But what you find is that if m is high enough, then suddenly this line moves to the right and not to the left. And so here I show you what happens now. This is now as function of system size for different values of m. So this is m equals 1 is of course always at PC, it doesn't move. And m equals 2, m equals 3. And what you see is that there is a characteristic value of m, which doesn't happen to be an integer, which happens to be 2.55, above which the transition moves to the right and ends up finally at p equals 1. Or below which it moves to the left and ends up at PC. Yeah? And of course then there must be also one value of m at which it doesn't move, which is exactly the middle, which is exactly the value of this one. Yes? And so now one can fortunately close the whole story with an analytic argument by using the scaling law that I showed you from the bridges of percolation. So here we come. This is the scaling law that I showed you and I asked you to remember. Yeah? And now what we do is the following. We say, in this model, we are only creating a spanning cluster if all m bonds that we chose are bridges. Because then we have to occupy one of the bridges and the system spans. So the probability to span is the probability to have a bridge to the power m. This is what is written here. So this is the probability to span is the probability to have a bridge to the power m. The probability to have a bridge is the number of bridges divided by the total number of bonds. The number of bridges divided by the total number of not yet occupied bonds. This is the total number of bonds, L to the D, and this is the fraction of bonds which are not yet occupied. Okay? And now I just insert here the scaling law. I put it inside. Yes? And then I can write here everything independent of L. Yes? I can take this out as L, and finally I get this expression here, in which now the system size is here, where NB is the number of bonds, which goes like L to the D, it's D-dimensional. So here you have L to the D to this power. And what you see is now I took an abbreviation, I abbreviated this MC is given by this expression here. And what you see now very easy from this way of writing it is that if this here is 1, then the system does not depend anymore on system size, which is exactly what we have here. I mean, this is the case in which this does not depend on system size is given when this exponent is 1. That means when m is MC. So this is exactly the expression for the critical m. This is the m at which this doesn't change anymore. And so this is actually, if you insert now here dB, which we have seen before, dB was the number we have calculated, 1.22. This is the famous number, yes. If we insert it here, 1.22 in 2 dimensions, 2.4 in 3 dimensions, we get exactly these numbers here. Oh, so everything is closed, yes. And we have to be able to prove that there exists a first order transition at a specific value in the, somewhere here, at which this guy does not move to the right and to the left, and this first order transition is in, I mean, you can calculate. Oh my God, sorry, everything. So this is the end of the story. So we have been able to prove here in this case for finite dimension that if m is large enough, the dimension is low enough, let's say, there exists a first order transition, and when you reach 6, then this is 6, and this is also 6, and this goes to infinity, and so above 6 dimensions we only have continuous transitions, which people that have proven that the transition is continuous for the product model will be happy. But again, people like Gliozzi who always believes that what is true for finite for mean field must also be true for the square lattice are wrong, because here I prove that it's different. And below dimension 6, and for m large enough, I do have first order transition. Good. So this is for me now the end of the story of, let's say, the product rule of the explosive percolation. I would like to show you another 2 pieces of work which we did afterwards, which show that this situation can be even more interesting. And the first one is now, and all these models, I think it's the same philosophy. I would like to make the first order transition, and now I will make my rule a little different. Namely, I would say, I will have, instead of saying I will suppress the formation of a large cluster, I will now say I will enhance the growth of the small clusters. I will try to not to leave small clusters, that all the clusters that are small can grow more. And for this I invent now the following law. I say I put all clusters, I divide all the clusters into two parts, the ones that are smaller and the ones that are bigger. And I introduce now a new parameter which I call G, which is the fraction that are supposed to be in the lower size cluster section. How much percentage of the clusters I put in this lower section. Okay? And now the rule I introduce is that whenever I want to occupy a bond, one of the two sides that I connect must belong to this class. So in that way I always connect a small cluster and make a small cluster larger. Yes? And G can be changed. This reservoir of the small clusters, what is this definition of what is a small cluster? I can change. I can make G very small, then of course the small clusters very easily are eaten up, or I can make G very large and then it's very close to classical percolation. Yeah? Okay, that's the model. I hope this was clear. And now I evolve, I just do this simulation, I just occupy bonds. And I find the following. For G equals to 1, that means that everybody is in this same box, then of course it's classical percolation. If G equals 1, then all clusters belonging to this family, and then I can do whatever I want. So for G equals 1, I have classical percolation. This is the red line. And when I now decrease G, I have, as in all other cases, I get this, I get a shift to the left, to the right, and I get this kind of first order transition jump. Yeah? And what is funny about this model? You can, if you do it in mean field, that means if you now allow connections between any cluster, yes, you just take clusters, put clusters in a big box, and you just take the clusters out and connect them. You don't think about the space. Yeah? Then you can solve this model, and you find that the transition is not just first order. The transition is a hybrid transition. It means you have a jump, but after the jump, you have a power law. It means that you have here a jump, let's say a blue line, and after that you have still a critical kind of behavior, and with an exponent beta. Yes? And then what is funny, and this is the only example up to now known of such a hybrid transition. So these transitions which are like this, you have a jump and a critical, let's say, increase of the order parameter after that, are called hybrid transitions. And there exist about 10 or 15 such examples of such hybrid transitions, also in long-range IFISC models studied by Mukamel. And here we have the only existing example in which now the critical exponent that you have after the transition depends continuously on the parameter of the model. In this case, it depends continuously on G. G was the only parameter of the model. And here I show you, especially, this is the exponent beta of the order parameter, but this is maybe not so easy to see, like the exponent of the cluster size distribution tau. So the cluster size distribution also has a power law, and it is proven in general terms that the exponent of this power law must always be between 2 and 2.5, so it's a very narrow regime. But what you can see is that for this model, yes, numerically you can get these taus, and you see that indeed they depend on G. You can even make a numerical plot, and you can see how it depends on G. This is here G, and this is here the exponent tau, so it depends between 2 and 2.5. But the fantastic thing is that you can also manage to derive an analytic relation between G and tau. And this is this relation here, where this zeta is the Riemann zeta function. So it's a highly transcendental complex equation that relates tau and G, but since this is analytical, there is no doubt that here we have a transition in which the exponent, a hybrid transition in which the exponent is continually varying as function of the parameter of the model. So this is what I wanted to show as another, let's say, exotic situation. And finally, then I would like to make another remark, which makes everything a kind of trivial remark, which everybody will immediately see it's trivial. This is 2014, so it's after all this. It's funny that this was only done after all this evolution. To make a long story short, everybody knows the Potts model, no? Potts model. Yeah. And everybody knows, hopefully, maybe, that the Potts model in 2 dimensions has a first order transition when Q is larger than 4, and the first order, second order transition when Q is less than 4. This is the Potts model. And now, there exists a very interesting paper, which nearly nobody knows about, by somebody called Gliozzi in 2002. And what Gliozzi shows is how you can, with a percolation model, produce Potts clusters for arbitrary Q. And so what he does is, he can prove, I mean, this, I don't want to go into too much detail, but the method is the following. You throw a random number between 0 and 1. Yeah? If this random, and you divide this interval between 0 and 1 now in 3 pieces, one of them is at the length p over q, and here this is at a height p. So q is of the q-state Potts model, so it's a number 1, 2, 3, 4 integer, and p is now the probability of percolation, so it's a number between 0 and 1. So p over q is of course smaller than p, and in fact for q equals 1, which is the Potts model, which is the percolation, they are identical. So there's one transition for percolation. And now what Gliozzi does, for everybody who has worked, you choose a random number between 0 and 1. If this random number falls in this interval, you occupy the site. If the random number falls in this interval here, you empty the site. And if it falls in this interval here, you occupy the site only if it belongs to the same cluster. That means that if it does not create a new connection between 2 clusters, only if it is an internal bond. And if you do this very, very simple procedure, Gliozzi can prove that you create the so-called critical clusters of the corresponding Q-state Potts model. And this, without going into more detail, shows that this is a direct percolation problem which you can do in order to produce first-order transitions if you choose your Q larger than 4 in 2 dimensions. So this is another example that of a first-order transition, which is kind of trivial for everybody who studies statistical physics, which can be, let's say, made clear. And I show you here that here you can show also that, I mean, Numerical has done it. You can show it analytically. You can also do more numerically, and you can show that there is indeed when you are close to this regime. I'm sorry, I mean, I don't want to go into detail of these numbers, but anyway, what you find is also numerically that in this case you have a bimodal distribution, etc., so that everything is consistent. So this was the remark. And finally, I would like to show another example of a first-order transition, which is more practical. I'm finishing in a minute. Don't worry. Which is an epidemic model, which, you know, the epidemics, let's say the contact model is related to direct percolation, so it is a relation to percolation. And this model is the following, very simple-minded also. It is the classical SIS model that everybody of you has seen many times, okay? With one detail, there's a small b in front, which means that we have a budget. It means that in order to heal somebody, you need some money. And this money comes from the healthy population. Okay? So that you have, in addition to the classical SIS, you have that whenever, that at every time step, the blue ones are the healed ones and the red ones are the sick ones. The ones that are healed produce a certain amount of money. And then at each time that you have to cure somebody that was sick to healed, you have to also get some quantity of money C, which you have to invest. And this model now can be simulated easily. And what you find is that there exists a critical infection rate. Infection rate is always the ratio of the probability to infect divided by the probability to heal. A critical infection rate in which the following happens. The system seems to saturate. I mean, you get the classical curve of SIS is that you have an increase on the sick population, and then there is a point at which it goes to some some value which is constant over time. But what is funny about this model is that in this case, it reaches a point and suddenly, oops, it goes to a so-called pandemic situation in which everybody gets sick. There's nobody gets saved. And the reason for this jump is, of course, when the budget is exhausted, then everybody dies. So this is the role of the budget. In some sense, it is very much related to what I said before, because if you look carefully in what I said before, the conditions that I introduced always in order for making this transition to be abrupt is a global condition. Always there is a global knowledge about spanning. Spanning is a global knowledge that you need in order to know if it doesn't span or not. And here again, there is a global budget. So this global knowledge is the one that produces the sudden pandemic regime. Okay, so here I finish, and I hope that it was useful for you. Thank you very much.
Thank you very much for this enthusiastic ride through percolation. I'm sure there's questions.
You don't be so sure.
Sorry. This idea of you need global information to get first order transition. My intuition is from dynamical system, not from phase transition.
Yeah.
But I would say that maybe just no local information, not global, but just around of a big piece would be enough to create the first order transition.
Yes, in the case of cooling is the case. Yeah. But in cooling, you have local information, but therefore you have this kind of not local repetition, you have the iterative scheme, which is essentially global again. And you have to iterate until all the sites with less than 2 neighbors are exhausted. What you can show is that when you come to the transition point, the number of iterations goes to infinity. And this is again global. Okay. But you have another case.
Maybe
yes.
whether the conditions is not just about the global thing, but the condition is about the region around you of certain sites. You get a link or not depending on the condition of certain sites around you. Wouldn't that create a first order transition?
I don't think so.
You don't think so?
No.
No questions.
Yeah, one of the ways to check that whether to do this first order is to for hysteresis.
Yes, yes.
I guess maybe you can compare that or whether it's some kind of way out. Here you could go from one information to another by varying the parameter. To create something with a new algorithm, you have to start from scratch.
You're completely right. So the models that I talked about are non-empirical models. And so the fact that I always go in one direction, I always occupy sites. You're completely right. If I want to look at hysteresis, I have to also define the back procedure which can be done. I can do every let's say every rule how to fill. I can invent a corresponding rule how to unfill. But I must really think about how to do it. So it's not canonical. The model itself is unable to show the going back. It's very good.
In your last model, is there a parameter associated with this amount?
Yes, the cost of individual helium.
And how does it depend, of course?
There's a critical cost above which you get in pandemics and below which you heal everybody. You heal certain functions. In fact, there are 2 parameters. One is the rate of infection, and the other one is the C. Here. One is this rate of infection, which is P over R,
right.
and the other one is the C. These are the 2 parameters of the model. Because this is unity. And every of these individuals is 1 unit of money, but then you have the C units to need to.
Okay.
So the relation between this and this, and the relation between this and this.
This is what I
So between this and this. Yeah.
So the last one is just 1 unit.
Yes.
No questions. I've actually one myself. I mean, you're playing fascinatingly with all these rules, right? And in the last part, you show one example where this could actually be applied, such kind of rules. Are there other examples where the rules that you define and that you play with could have, let's say, practical relevance in nature, or could be used in, for example, this could be science, let's say, health politics or anything, that these rules have practical relevance?
Yes, this is not the only example, for instance, for an epidemic model which has abrupt behavior. We have other cases in which there are other kind of rules which are non-local. Yes. So, but for instance, this is, I don't know of any model, for instance, for the dam breaking or for the volcanoes. This is still has to be done. It's a challenge for the future.
Okay, thank you. Maxim.
There have been also a number of papers, either percolation or diffusion in multi-layer networks.
Yes, of course, like that.
Where again there is a discussion if the discussion becomes first order or not. And can you say something on that?
Yes, in the multi-layer case, there was this work by Herrmann et al.
There are a number
Which
of
prove
papers.
that the transition is actually first order in midfield. When you have this rule of collapse, that you say there are two networks in which every side of one network has to be connected to the side of the other network. And then if one of the two sides fails, then the whole side fails, and the other also fails. And then the other condition is that all sides in one network must be in one big cluster. And each time you disconnect one of them, then you also remove it. And with this rule, you create a kind of cascading failures. And so if you introduce that, then you create the first order transition because you squeeze actually by doing this kind of a procedure, you squeeze the axis from both sides against PC. So it is very similar in some sense to the spirit of pulling, of bootstrap percolation. Because you do this cascading in this iterative process, you break some bonds, you remove, and then some others get isolated, have to be removed. So what can be shown is that also in the case of multi-layers, the number of iterations that you have to do at PC is infinite, goes to infinity. And so what you have is you have originally a transition like this, and now you are squeezing the axis on both sides more, and then of course what you do is you make this more and more steep until it becomes a first order. So the first order transition in these multi-layered networks, which actually has only been calculated for two networks, I mean for two layers, never more than two layers, is essentially like bootstrap percolation.
So it's not associated with this idea of global and local.
It is global, yes, it is global in the sense that you have to make an infinite cascading procedure, yes, and then that way you can communicate information to infinity by doing a number of iterations. So in some sense it is global behavior, but it is not that you suppress the largest cluster systematically or so. This is not what you do.
Are there more questions or comments? If that's not the case, let's thank Hans once again.
So, danke schön. Danke. Orazio, espero que nos veamos pronto otra vez. Tienes que aparecer en la televisión una vez se la acelera, ¿no? Entonces vaya. Esta vez no voy a poder ir
Voy a tratar.
Claro. Aprovechen los tiempos.